Welcome to the second video on the various renewable energy technologies. In this video we'll consider the physical principles behind solar power and biomass, as well as their advantages and limitations. We will start with solar energy, one of the most flexible and fastest growing technologies available. We'll discuss two technologies to generate electricity from solar radiation, namely photovoltaic and solar thermal technologies. In photovoltaic energy conversion, the light emitted from the sun is absorbed by the semiconductor materials in the PV panel. The semiconductor material converts the light's energy directly into electrical energy. The panel is connected to an inverter that converts the DC output of the solar panel to AC power and facilitates a grid connection. Since there is only a single conversion step in photovoltaics, from light to electrical energy, losses in the PV system are limited to the PV panel conversion efficiency, transport losses in the wires and cables, and the losses in the electronic components such as the inverter. Later in this course we'll discuss all the losses that occur in a solar cell in detail. The physical principles for solar thermal energy conversion are much different. Light from the sun is absorbed by panels and converted to thermal energy. Liquids within these panels are heated up and go through a heat exchanger to heat up a second liquid, such as the water in your house. In rooftop applications, solar thermal technology essentially replaces some of the energy that you would otherwise use to heat up your boiler. For commercial applications, the heated liquid is used for electricity generation as well. Small-scale parabolic solar concentrators like these use a large area of mirrors to concentrate the light to a small tube. The liquid in these tubes will become hot enough to boil water, after which a conventional steam turbine is used to generate electricity. The same principle can be applied on a larger scale, as shown in the concentrated solar energy towers in this visual. In some commercial solar thermal power plants, molten salt is used as a working liquid, which can heat up to more than 500 degrees Celsius. A big advantage of these salts is that they can be stored and the heat can be utilized during the night to produce electricity. This makes the power generation less intermittent. Solar energy has many advantages. For one, the energy potential of solar energy is more than 1,000 times the average global power demand. Additionally, the modular nature, small unit size, and low unit investment make PV easily scalable and ideal for remote and developing locations. Moreover, PV these days is generally a sound economical investment, with system payback times in the range of 3 to 7 years depending on location, and system lifetimes of over 25 to 35 years. The limitations of PV are related to the day-night and seasonal fluctuations of solar radiation, which results in a relatively low capacity factor and power generation intermittency that is challenging for grid stability. The next renewable energy technology we consider is power generation from bioenergy, which involves the burning of biomass or carbon-based fuels from biomass in a power plant. As with the previous technologies, biomass starts with the sun. All plants and trees on Earth use photosynthesis to convert solar energy into chemical energy, in the form of carbohydrates. The biomass is stored and then burned for either heating or for the generation of electricity using a conventional steam turbine generator. Bioenergy exists in a lot of forms, solids like wood, but also liquids and gases. Crops like sugarcane and elephant grass, for instance, are produced to make liquid biofuels. Additionally, methane can be produced through the gasification of biomass or through the fermentation of the manure or livestock like cows and pigs. Methane obtained through these routes is referred to as synthetic natural gas or biogas. The advantage of biogas or biofuels with respect to unprocessed biomass is the higher energy density, which makes storage of biofuels easier. Consequently, a big advantage of bioenergy is that it can be stored. Secondly, biomass can be burned in conventional power plants, and certain biofuels can also be used in existing infrastructure, such as cars, planes, and residential heating systems. Integration of these biofuels therefore requires minimal changes in the energy infrastructure. Additionally, the energy density in most biofuels is much higher than in other means of energy storage, including batteries or molecular hydrogen. Biomass also has a number of significant disadvantages. The first generation biomass, such as sugarcane, is in competition with crops cultivated for food in terms of land and water use, which are increasingly rare commodities. It should be noted this is not the case for biomass obtained from waste streams and certain types of biomass, such as the algae shown here, or crops cultivated off the coast. These applications generally have their own respective challenges, however, related to poor scalability or relatively energy-intensive collection and/or harvesting. Additionally, the net energy gain of some biofuels can be very low. The energy balance of converting crops into liquids, like bioethanol, can even become negative. This means that more energy is used in the processing and transportation, land use and fermentation than is finally stored in the biofuel. These aspects affect the carbon footprint of bioenergy, which is very high in reference to other renewable energy technologies. Finally, and most importantly, while biomass can provide a renewable source of energy, it is definitely not a clean source of energy. The burning of biofuels produces greenhouse gases, which contribute to climate change. Moreover, the poison and fertilizers used to grow the crops have significant adverse effects on the environment. These images from NASA and the European Space Agency show inconceivably large dead zones in the Baltic Sea and Gulf of Mexico. These dead zones are the result of agricultural runoff, pollution of these seas with nitrogen and phosphor, which result in a toxic algae bloom that extracts oxygen from the water and kills all other organic life. This concludes the second part of our overview of renewable energy technologies. In the third part and the final part, we'll look at the geothermal power generation and compare the various energy technologies using some different metrics.